Hello everyone. Imagine you're in a car that speeds up smoothly from a traffic signal. You notice that the speed doesn't jump suddenly, but increases steadily every second. This is what we call uniform acceleration. In physics, when an object's velocity changes by equal amounts in equal intervals of time, we say it is moving with uniform acceleration. A classic example is free fall under gravity. Every second, the velocity increases by about 9.8 meters per second. Such motions are not only fascinating but also predictable. And to understand them, physicists derived three simple but powerful equations. Today, we'll carefully go through these derivations step by step. As you see in the velocity time graph here, the slope remains constant, which represents uniform acceleration. Let's begin with the very first equation of motion. Suppose an object starts with an initial velocity denoted by u. After time t, with uniform acceleration a, its velocity increases. The change in velocity is acceleration multiplied by time, that is, delta v equals a into t. Adding this change to the initial velocity, we get the final velocity v. So mathematically, v equals u plus a into t. This equation directly connects final velocity, initial velocity, acceleration, and time. As you can see from the velocity time graph, the slope is constant and the straight line shows how velocity increases linearly with time. Now let us derive the second equation of motion, which relates displacement with velocity, acceleration, and time. Displacement is simply the area under the velocity time graph. For uniformly accelerated motion, the graph is a trapezium, a rectangle plus a triangle. The rectangle's area is u into t. The triangle's area is half into a into t squared. So total displacement, denoted by s, becomes s equals plus 1 by 2h squared. This elegant formula tells us exactly how far the object has traveled in a given time under constant acceleration. In the diagram, notice how the shaded area under the velocity time curve represents displacement. Next comes the third and most powerful equation. This one eliminates time altogether. We know acceleration equals open bracket v minus u close bracket divided by t. From the second equation, displacement s equals ut plus half h squared. By carefully substituting for t and simplifying, we arrive at v squared minus u squared equals 2as. Finally, the relation becomes v squared equals u squared plus 2as. This equation is especially useful when time is not known and we only want to connect velocity, acceleration, and displacement. To help visualize, look at this derivation flow. Each algebraic step connects back to the definitions of motion. Now that we have all three equations, let's pause and reflect on their meaning. The first equation, v equals u plus at, predicts the future velocity of a moving object. The second equation, s equals ut plus half at squared, helps us calculate the displacement during that motion. And the third, v squared equals u squared plus 2as, directly relates velocity to displacement, bypassing time altogether. Together, these are called the kinematic equations of motion. They form the foundation for analyzing motion, whether it's a car on the highway, a stone in free fall, or even a spacecraft lifting off. Let's test these equations with a numerical problem. A car starts from rest with acceleration 2 meters per second squared. We want to find its velocity after 10 seconds and the distance covered. Step 1. Apply the first equation, v equals u plus at. Here, u is 0, a is 2, t is 10. Substituting, v equals 20 meters per second. Step 2. Apply the second equation, s equals ut plus half a t squared. Again, u is 0, so displacement equals half into 2 into 10 squared, which gives 100 meters. Step 3. Verify using the third equation, v squared equals u squared plus 2as. Substituting, 400 equals 0 plus 2 into 100. both sides balance, correct? This shows the consistency of the three equations and how they interlock beautifully to describe motion. So to wrap it all up, under uniform acceleration, we derive three fundamental equations. V equals u plus a t, s equals ut plus half a t squared, and v squared equals u squared plus 2a s. We derive them using both algebra and geometry from the velocity time graph. These equations form the backbone of kinematics and are applied in countless real-world problems. From calculating how long it takes a train to stop to predicting the path of a ball thrown upward, these equations are everywhere. I hope this session has given you a clear picture of how motion under uniform acceleration is not only predictable, but also beautifully mathematical. See you in the next class, where we'll apply these equations to freefall and projectile motion,